5.10 Carnot Cycle. The Carnot cycle is an ideal cycle. It is a reversible cycle. It is the most efficient cycle between the two thermal reservoirs, as it is a reversible cycle. The cycle was suggested by a French engineer, Sadi Carnot, in 1824. It sets the maximum possible thermal efficiency of any real power cycle between the two thermal reservoirs. It exchanges heat with two thermal reservoirs. High temperature reservoir at temperature TH and low temperature reservoir at temperature TL. So it consists of 4 reversible processes, 2 isothermal heat transfer processes, and 2 adiabatic processes. So let's see the Carnot cycle in a piston cylinder device. It is a closed system. It is continuously operating, going through 4 processes: adiabatic compression, isothermal expansion, adiabatic expansion, and isothermal compression. It is a thermodynamic cycle, so the device returns to its initial state at the end of each cycle. The 4 processes in the Carnot cycles are illustrated in a pressure specific volume diagram. This is a constant temperature line at temperature TH. Another constant temperature line, temperature at TC. So they are the temperatures of 2 thermal reservoirs. There are another 2 lines describing 2 adiabatic processes. So this line and this line describe 2 adiabatic processes. So let's take a look at each step in detail. So first, process 1, 2. Reversible adiabatic compression. So adiabatic indicates the system is insulated. So Q is 0. Work is done on the system, causing the piston to compress. The specific volume decreases from V1 to V2. The temperature increases from Tc to Th. Process 2-3. Reversible isothermal expansion. Insulation from the system is removed, and heat from the high temperature reservoir is transferred to the system, that is QH. The gas inside the system expands and does work on its surroundings. The gas pushes against the piston. The specific volume increases from V2 to V3 while maintaining the temperature constant. So the specific volume increases. And it's a constant temperature process. Imagine that the system is in direct contact with the high temperature reservoir and maintains a thermal equilibrium with it. Process 3-4. Reversible adiabatic expansion. Again, the system is insulated. It is an adiabatic process. So no heat transfer during this process. Q is 0. The gas continues to expand and do the work on the surroundings. The specific volume increases from V3 to V4. As there is no heat addition to the gas, the internal energy of the gas decreases. The temperature of the system drops from TH to TC. Process 4-1. Reversible isothermal compression. Again, the insulation from the system is removed, and heat is also removed from the system. That is QC. Imagine that the system is in direct contact with the low temperature reservoir. The work is done on the system, causing the piston to compress. And the specific volume decreases from V4 to V1. And this completes the cycle. The area under 2-3-4 curve is the work done on the surroundings. The area under 4-1-2, this is the work done on the system. So the area enclosed by 1-2-3-4-1 represent the net work produced by the Carnot cycle. So this is the net work produced by the Carnot cycle. There are assumptions for the processes in the Carnot cycle. First, there are no irreversibility present in the cycle. No mechanical frictions. Heat transfer occurs across infinitesimally small temperature difference. And heat transfer is a reversible process. The temperature of real systems experiences continuous change of temperature during the process. But what we assumed in Carnot cycle is quasi-equilibrium heat transfer. Second, the system has a perfect insulation during the adiabatic process. There is no heat transfer during the adiabatic process. The system is also a perfect conductor during the heat transfer process. Third, the compression and expansion processes are reversible. But it is not possible to build a Carnot cycle. First of all, we cannot build reversible cycles. Besides, the process should be extremely slow during the isothermal expansion or isothermal compression processes to achieve quasi-equilibrium heat transfer. On the other hand, the process should be extremely fast during the adiabatic expansion or adiabatic compression processes. We can apply the Carnot cycle to the open system. The Carnot cycle may consist of several components, as illustrated here: pump, boiler, turbine, and condenser. It also undergoes 4 reversible processes. Heat is transferred to a boiler reversibly and isothermally. Work is done by a turbine reversibly and adiabatically. Heat is transferred from a condenser reversibly and isothermally. Work is supplied to a pump reversibly and adiabatically. The thermal efficiency for the Carnot cycle is W net over QH. So which is desired output divided by the required input. So we apply the first law of thermodynamics. W net is QH minus QL, which is 1 minus QL over QH. So QH is the heat supplied by the high temperature reservoir at temperature TH. QL is the heat rejected to a low temperature reservoir at TL. So thermal efficiency becomes 1 minus QL over QH. According to Kelvin temperature scale, QL over QH is TL over TH, so absolute temperature ratio. If the Carnot cycle runs in reverse direction, the device becomes a refrigerator or a heat pump. W net is the required work to transfer heat from a low temperature to a high temperature. So W net is the area enclosed by 1, 2, 3, 4, 1. QL is the heat absorbed from a low temperature reservoir at TC. And QH is the heat rejected to a high temperature reservoir at TH. So the coefficient of performance of a refrigerator is TC over TH minus TC. The coefficient of performance of a heat pump is TH over TH minus TC. So TH and TL are absolute temperatures. The actual irreversible cycle will have smaller thermal efficiency. And if the thermal efficiency of a cycle is greater than that of the Carnot cycle, it is impossible.